Just waiting for this gentleman to... Don't rush. We'll wait for you. It's waving at me. Morning, Kelvin. How are you? Good lad. Didn't see you this morning. I was getting worried. I was up there at 4:30. She's waiting for a sale. Well. There's a few more. My watch has been forward and back. And I had to ask this lady up here, what time is it? Nobody's here. Is it 9:58? Oh, we're a bit early. Anyway, we'll just chat. Good morning, everybody. Can you hear me at the back? In the cheap seats? Good luck. Good. I'm Robert Brown. Good morning. I was talking to a lady this morning at 4:30 up on the smoky platform up there. And, just before that, sorry. This is the 6th presentation in a series of 7. Alright, so we've got 1 to go. So tomorrow, I would expect everybody is looking forward to getting off this ship. I am, so I would imagine you are. So there's no lecture tomorrow, talk. The next one is on Saturday. That's the final one. Alright? So, I'll come back to it. I was talking to a lady upstairs on the smoking deck at 4:30 this morning. I think she's in the audience. I've just seen her. There she is. And she says, my husband likes electronics. He's got one of them Spectrum things. Now, a Spectrum, and his proper name is a ZX Spectrum, was one of the first personal computers that we had in the UK. We also had a Commodore 64. Yeah? Can you remember them? I had one of them. Back in the UK, you were either a ZX Spectrum man or you were a Commodore 64 man. It were a bit like General Motors and Ford, you know what I mean? Anyway, at that time, computers were in their infancy. And I've been quite privileged as an engineer to see the rise of computers from the first introduction to what they are now. And I thought this would be interesting, this slide. So, when I was a boy, a young engineer, I used to work on these things, Norlogs, which was basically a little green block, and that represents 1 bit. Not a byte, a bit. So that had 2 states. It was either on or off. And if you don't know, computers work in a binary notation, which is mathematics in base 2. We all work in monetary systems in base 10, decimal. So that represented 2 states. It could either be on or off. Now, when I was a young engineer, we had computer rooms about as big as this, and it was full of green-like, wardrobe-like cabinets, and in there were racks and racks of these things. And there'd probably be on 1 rack 32 of these, so that represented 8 bytes of memory. Yeah? Now we're down to this, and that's a full computer system. Yeah? Further, I make it back. In 1956, this is a 5 megabyte hard drive. Yeah? Now, fortunately, I hadn't been born in 1956. But I can remember in the steelworks where I worked as a young engineer, we had one of these delivered, which were was about a quarter of the size, and that had got 4 megabytes of memory. And it was that special that it got its own, we dedicated its own room to it, which was air conditioned, it had carpets in it and things like that. And when we went, it got windows and we used to press his nose against it. We were a bit like watching this thing in operation. Real technological advance. Now we're down to something like that. That's got 1 terabyte of memory, and 1 terabyte is 1,000 million bytes. So in terms of bits, that's 8,000 million bits. Yep. The computer rooms were as big as this. And these things here are the hard drives, and you can see on the top these like disk things. They were the disks that actually went into the hard drives. So, being a bit of a nerd, I counted these up, but I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like 15. Yeah. So that was real. So I think at 4 megabytes per drive, that represents 60 megabytes of memory. So now we're up to this. So if you consider that 1 terabyte little thing, and imagine how many are in that, and how many cabinets we've got, massive computer difference in my lifetime. So we come to this, today's talk. Mr. Marconi, you've copied our invention. This is what we'll go through to today. And I'm going to develop this talk. So, Mr. Marconi was an Italian gentleman, famous for radio and wireless. Now, he didn't invent the wireless. Marconi, Guglielmo Giovanni Maria Marconi, an Italian guy, was an entrepreneur, businessman, and he developed the use of wireless across the world and made much money from it. So you could say in a fundamental sense, he stole somebody else's invention. Respectfully, he didn't, he just capitalised upon it. So, what are these? How do you know the magnets? Because it says up there, magnets. Yesterday I spoke about this garden jewellery heist. Now, when I went on the stand to give evidence, Richard Sutton, the defence barrister, put up on a big screen like this pictures of electronic equipment, and these pictures had been generated by my counterpart on the prosecution. And he'd annotated certain things on these pictures, like a power supply or resistor or relay. And Sutton got these pictures up, and he went through these things, and he got to one particular component which looked like a white block. And he said, well, Dr. Brown, what's the white block? And I said, oh, that's a relay. And he said, and how do you know it's a relay? And I said, because it says it is. So, these are magnets. In the UK at Christmas, I will get there eventually. In the UK at Christmas, we have these things on the Christmas dinner table called Christmas crackers. Do you have them in the UK? Sorry, in the US? No, I'll describe them. They're like 3 cardboard cylinders, and they're conjoined end to end, and then they're wrapped in all nice Christmas foil paper. And through the centre of it is a snap cracker. So when you pull it, it cracks. Yeah. In the centre cylinder, there's usually 3 things. There's a hat, Christmas hat, that only grandmother or mother wear because they're awful and they never fit. And then it also, there's a motto or a joke, which are terrible, and that goes straight in the bin. Might as well save the forest and not put that in. But then there's a novelty, and the novelty is usually like a Chinese puzzle, or it could be a really awful plastic ring that nobody would ever wear. If you were lucky, it might have got a little water reservoir behind it, so when you pushed it, it'd squirt water out. But sometimes you were lucky, and you'd get this magnet. And even if you were more lucky, you might get two. So then you could do a little bit of experiment and understand that like poles repel and opposite poles attract. Yeah. So these are, as it says, magnets. When we were in science lesson at school, we may have done this experiment where we poured iron filings on these things. And what this is showing us in 2 dimensions is the magnetic field that exists around a bar magnet. In 3 dimensions, it could look like a rugby or an NFL ball. But this is showing us in 2 dimensions because it's flat. What that doesn't show us is the direction of the magnetic field. All it shows us is, in this case, it's flat and the pattern it creates. But if we look at this diagram, we can see that that pattern indicates that the lines of magnetic flux leave a north pole and enter a south pole. Yep. Always done, a fundamental law of nature. Now the Earth has got its own magnetic field, and the reason for that is way below us in the core of the Earth is molten iron, which generates this magnetic flux. Now can you see something fundamentally bemusing between those 2 diagrams? I've heard a few mutterings. If we look at the lines of flux on this one, they're coming this way, and on that one they're going this way, although we know that's the North Pole and that's the South Pole, South-North. So, in fact, in a correct sense, the Earth's South Pole is at the North Pole, South Pole magnetically is at the North Pole, and magnetically the North Pole is at the South Pole. I didn't know that until a few years back. I found that really interesting. So, we understand from that lines of flux leave a North Pole and enter a South Pole. Now, in an electric wire, when we pass electrical current through electrical wire, the fundamental law is that it will generate a magnetic flux which permeates out at right angles, or in a mathematical sense, orthogonal to. And if we look at that, we've got electrical current going from left to right, and we've got this B, which is its magnetic field. So if I use my right hand, this is referred to as Fleming's right hand rule. This is the direction of the current, and my fingers are showing you the direction of the magnetic field. Yeah. So if we were to coil up this wire in like this, we would, in an electrical sense, generate this bar magnet, and it would, near as possible, have the same characteristics in a magnetic field. Yeah? So, if we just expand that a little bit further, if we've got this bar magnet and its magnetic field around it, if we were to physically push that bar magnet near a coil of wire, it would generate an electrical current which would be measured on this little meter. So if we went like that, we'd see that flick backwards and forwards. Yeah? Now, we take this a little bit further. If we drill a hole through the centre of our bar magnet like that, and we start to twist it, we're generating a rotating magnetic field, right? And if we brought a wire to get close to it, we'd see this. That'd be flicking backwards and forwards, and on a sort of like a heart monitor, if we monitored it, we'd get that. Now that, if you agree, is the basis of an electrical generator. We generate an electrical current. Now, if we were to put a little turbine on the end of there, and we move that under a tap, together we've created a hydro plant. So running water causes the turbine to go around and we generate electrical current. Right. So I've got a little video for you now. And so we've got an electrical generator, and bear with me, I'm going to try and get this to work. So, this is interesting. So what he's doing is he's applying a magnet on top of the battery. This is a coil of wire. So what this is an electrical motor. So if we put a turbine on one end, we've got a fan. And what's happening is the electrical current's going up there through the coil, which is generating a magnetic field, which at certain points opposes this magnetic field, the repulse, and it provides physical movement. So together we just developed an electrical motor. Yeah.
Just seen that.
We've just seen that. So, you might have heard of this called a transformer. And this is just a little bit more application of what we've been talking about. In that here we have a primary coil, just a simple coil. And here we have basically, they refer to it as a transformer core, but it's just a square piece of iron. And the magnetic field generated when we pass current through this one revolves around there, passes that one, and because it's cutting these, magnetically interfering with these wires, it generates a secondary current which lights the bulb. That's a simple function of a transformer. You may have heard if someone's been doing DIY, I want a step up or a step down transformer. So in a transformer you can supply with 120 volts and generate 240 volts up, or you can supply it with 120 volts and step it down. There's all different combinations. Those laws were first introduced or discovered by this guy called Michael Faraday, and they're referred to as Faraday's laws of induction. Faraday was the Flugian Professor of Physics at the Royal Institution in London. The Royal Institution is on Abermyle Street in Mayfair in the centre of London. So if you're walking down Piccadilly from Piccadilly Circus, you come to the Ritz Hotel, and opposite the Ritz is a street that goes off orthogonal to a there's a royal institution. At Christmas, famous scientists gave lectures to children called the Children's Christmas Lectures, where they present their fields of research at a level that children can understand. These are televised, and I can remember watching these as a kid. David Attenborough did one on zoology, and you get these other, Professor Eric Laithwaite from Lancaster University. He presented at the Christmas lectures the first linear induction motor. Now, linear induction motor uses the same principles discovered by Faraday, but not in a rotational sense, in a straight sense. So now, because we've got the technology to further advance that, we get in the trains called maglev, magnetic levitation. And I would no doubt that if you went on these fast roller coasters that suddenly boost you up to a fantastic speed, that's all through to linear induction motors. Possibly bullet trains, yeah. Faraday, there's a statue of Faraday here. This is the headquarters in London of the Institute of Engineering Technology, or the Institute, formerly the Institute of Electrical Engineers. You can go in both these buildings, the free access and the nice buildings, just to enter the history of science. So, what I'm interested in is we developed together an electrical motor and an electrical generator, and we saw this sine wave being generated. And it's a sine wave because we'll be generating a rotational magnetic field. If I was to get a heart monitor and plug it in a socket, safely plug it in a socket, let's say down here or wherever in your room, you would see this waveform. And we're interested in this. This is the frequency of that waveform, the number of recurring patterns or periods per second. Now, in the United States, you will have a system 120 volts, 60 hertz, which means that that is occurring 60 times per second. Yeah? In the UK, we have a system 240 volts, 50 hertz, which means that it's rotating 50 times a second. Or in a reciprocal sense, one period is 20 milliseconds, quite fast. However, in electronics, we can reduce that period down to kilohertz, megahertz, gigahertz, and we're talking millions of times a second. Yeah? So, here we've got a wire, and it's conducting electricity current, and we're generating this magnetic field. And as we generating this magnetic field, at low frequencies, 50 hertz, the magnetic field can expand and then decay. So we're getting this effect, right? As we increase the frequency, because it's getting faster and faster and faster, this magnetic field doesn't have time to expand and decay. It starts to proliferate, permeate out. That's the basis of a radio transmitter. And any communication system is done through electromagnetic radiation. So now we've done that foundation, we come to this, the case. Does everyone understand so far? Good. So, this particular case, Weatherford Global Limited versus Oilpath Holdings Limited. I'll get into the crux of the case in a minute. This was heard at the Royal Courts of Justice, and this building is on the Strand. The Strand is a long street in London that emanates out from Trafalgar Square. And this is towards one end. And the Royal Courts of Justice is a beautiful building, and it's the site of many different courts. There's the High Court of London held in there, the Court of Appeal, there's a Crown Court in there, and then there's other divisions like the one that heard our case, which was the Construction and Technology Division. In that particular court, the judge and the barristers, they're not scientists, but they have a certain knowledge to understand the proceedings that's going on. You can go into this building, it's free of charge. This is the Great Hall, a wonderful building. There's all different artifacts that you can walk around and have a look at. And obviously I've been in there. And this is me in there. I find these interesting, electrical systems. I'm not bothered about this. I'd be just looking at that. But it's also been the film location of many films, and this one, Bridget Jones' Diary, and the other films in that series were all filmed at the Royal Courts of Justice. So, this particular case focuses on a piece of equipment. And this piece of equipment was manufactured and distributed by Weatherford Global. Does that look familiar from the diagrams that we've just looked at? What this is, it's a line scale reducer. So water had passed through the pipe, water has minerals in it, line scale accumulates on the inside of the pipe, reduces water flow. There's many different variants of this particular product, but basically we pass electrical current through this coil, generates a magnetic field, excites the atoms within the water, so it's given them energy, so they've got a less propensity to stick to the sides of the the pipe, and they flow through. Nice bit of kit. Now, Weatherfield were interested in applying this technology to a different market, and that was the oil market. Because in oil pipes, as we pass crude oil through a steel pipe, one of the byproducts of oil is paraffin, and particularly paraffin wax. And so there's a propensity for paraffin wax to accumulate on the inside of the pipe and reduce oil flow, which is a major down thing. Costs a lot in the production because it has to be cleaned out, etc. So Weatherfield thought, well, we can use this technology and we can put it into the oil industry. They were working in the domestic market, they got no leads into the oil market, so they thought, we'll approach somebody who has. And they approached this company, MSL Oilfield Limited. They're based in Southampton, on the cruise port, in the south of London. And they produce various oil field items. And they decided to collaborate together and develop this particular product to reduce paraffin wax accumulation. So for a few years they did. And they came up with this product, Clearwell. So this product basically consisted of a box of electronics which generated an electromagnetic field of high frequency. And they applied that signal to this thing, which fundamentally was a ferrite ring. And it spanned the circumference of the pipe, the steel pipe. And it worked. It reduced the accumulation of paraffin wax in this pipe. Now, after a bit, and they got this into the market, they found a fundamental problem by chance. And the problem was that if you physically moved this ferrite ring on a steel pipe, I'll just tell you, this combination is a transformer of one winding there, and the pipe itself being the secondary winding. That's how it worked. The problem was that when you physically moved this along the pipe, it sparked. Now, exactly, Kelvin, in a petroleum wellhead, a platform out at sea or in some oil distribution centre, that's a major problem. So, we'll come to this in a minute. MSL said to Weatherfield, this product you've developed sparks. And the guy who'd invented their product and developed it, and I developed products myself, was very passionate about it. Sure, baby. No, it does not spark. It does what you're going to do about it. It does not spark, we are doing nothing. So, you can imagine that MSL would introduce this company to their clients. They were in a poor position because it put them in a bad light. We've got to do something about this. So what they did is they developed it so it didn't spark. And they developed it in a way, by chance by the way, that what they'd done is they developed an aerial, an antenna. So they were using the length of the pipe, whichever direction that's going in, and they fed it with a high frequency signal which generated this electromagnetic thing that propagated out. But also in the pipe, it'll propagate into the pipe, excite the atoms in the petroleum oil, and stop the generation and accumulation of paraffin wax. That's what they did. So when they got this thing working, Weatherfield said to them, "You've stolen our invention." "No, we haven't. We've developed, this is totally different technology." So that's the basis of the dispute. And we all went to the High Courts of Justice and we discussed this. Shouldn't have shown you that. Anyway. I'll tell you why we will in a minute. But this is one of the very first cases that I actually went to court for, and it was interesting for me. And there was Weatherford, where the company who brought the claim, and there were 4 defendants. So in this courtroom there were 5 barristers. And they all sat at the front by the bar, and behind them are the solicitors, so there'd be 5 or 10 solicitors. Behind that there'd be the expert witnesses and the clerks and that. And I always remember this, that there was that much paperwork that in a morning they used to wheel it in on trolleys. We had lever arch files which were all indexed, and we got that many lever arch files. It went A, B, C up to Z, and then there were another section which were A, B. So there were several forests, and each barrister had got a set, the judge had got a set, the guy in the box had got a set. And whenever you were being cross-examined, can you turn to volume K, page 33, so you turned around, got this. Could you have a look at diagram such and such, whatever. Now, what was interesting for me is I watched people being cross-examined, and as I explained yesterday, it's a game of chess and it's really strenuous, and you really have to think what you're doing. And I remember they got this guy on the stand who was an eminent engineer, scientist, and there was a young barrister, and we'll call him the scientist Mr. Rogers. And the barrister said to him, "Now, Mr. Rogers, I want you to consider this circumstance." And he went, "Now, if this," I can't remember exactly, "if this and this, and we did this, would you agree it would do this?" And you could see the fear come into this guy's eyes, because he knew there were only two answers, yes or no. And if he answered yes, that compromised him, because it went against his team. So he sort of like went, "Well, this and this would do this and this and this," and he were expressing himself physically, but not answering the question. And after he'd finished, the barrister went to him, "Thank you very much for that, Mr. Stevens, but you have not answered my question. So I will put it to you again. Do you agree that if this, then this?" Same thing happened. "Well, it's this type of thing." And after this, the judge, spectacles down again, "Mr. Rogers, counsel has now asked you this question, the same question twice, and I think he's looking for a yes or no answer. So I will ask you the question. If you can't do, and he went through it again. And at the end, this guy goes, "Yes." And you went, "Thank you." That was it. I thought that was absolutely brilliant. Brilliant. The way the barrister had put the question, he could only have answered yes or no. Oops. So, we won. The judge decided that the intellectual property had not been stolen. In fact, the two products were distinct in a technology sense, in that the first product developed by Weatherford was a transformer, and the second product developed, or which came out of it by MSL Oilfield Services, was an aerial. And it's all the different, basically it's the different way that we utilise electromagnetic radiation. So, that's the end. Does anybody have any questions? No. Kelvin's always got a question. I see him in the morning, I say, "You ask me this question if nobody says anything."
In your professional capacity, what is the furthest abroad you ever had to go to testify as an expert witness?
I've not actually testified in court abroad, but I've travelled abroad extensively to work, and the furthest I've been is to Oman in the Middle East. And we were called across there because in Oman there's no natural water supply because it was in the middle of the desert. So all the water has to be desalinated from the sea. So along the coast they have numerous desalination plants. And to power these desalination plants, there are big electrical generators. So it's not a hydro plant, no water. So basically they have big diesel engines, which they fire up when it rotates, and this transfers its engine energy to a big alternator. And these alternators were approximately, I should say, 5-6 meters in length and 3-4 meters in width. So a big cylinder and an alternator, just like this, as we've seen, has an inside which we refer to as the rotor that spins round, and outside of that we have some more electrical windings which are the field windings. So just in that big thing, the outside, we produce a rotating magnetic field, and that magnetic field makes the armature in the middle rotate. Now, the electrical wires in this big thing were copper, and they were basically a centimetre square, and they'd be 6 metres in length. So they go down and then they come back. You get the idea, and they produce this big, basically big copper cylinder full of wires. And each wire would be insulated with fibre tape. So it's basically like a glass fibre tape. And then they'd be put into insulative slots. So due to magnetic forces, they couldn't attract each other, right? Due to this rotating magnetic field, the interaction with this is the rotor, there is a little bit of movement. And because the desalination plant is aside the sea and it's in the desert, when we cooling these things down, it'll pull in salt water. Salt saline is a conductor. It'll pull in sand, and over time, because of this movement, we get degradation of the fibre, and then we get, because there's open conductors, open coppers, it can electrical arc between them, which has happened in this occasion. So at this particular circumstance, they got 2 of these sets, and both of them had failed within 2 weeks of each other. So that fact itself, you think, that ain't right, there's something wrong here. So we went across, and we actually climbed inside these things, and we took all sorts of different samples, and then we said to them, can we have a look, can we inspect the air filters for these generator sets? And they brought out these air filters which were basically cylindrical, and they were wrapped in fibre. So you pushed air through them, and it filtered its way through this fibre, basically like cotton wool, and you got clean air out. And they brought these out, and they were the cleanest filters you have ever seen. They were obviously not those that had been used in situ at the time. They'd been tampered with. But as forensic engineers, we could say, look, these are not right. We just have to accept what they're showing us. And no doubt the loss adjuster from the insurance company were thinking, I'm going to reduce my offer now. But that's the furthest one that I've been to. I went to Istanbul, been to Paris and Munich, as we talked about. So I get to travel a little bit. So we've got a day off tomorrow, and on Saturday I thought what would be nice to do was I'd introduce some general talk about some of the idiosyncrasies and some of the unique cases that I've done, which I find interesting. There's little anecdotes in there about cross-examination and some of the things that are amusing in court, and the circumstances of the case itself are very unique and interesting. We'll talk about these courts again, particularly the Old Bailey, which has a really checkered past and things like that. But anyway, that's on Saturday morning at 10 o'clock. Thank you for coming today. I really appreciate you coming. And I hope you enjoy. I think I put it on here. Look at that. Somebody asked a question. I can't tell you that. I will find that out for you, and I will put it on the next presentation. But I don't think they can accredit it to one person. There were a lot of people working on it at one time, and somebody, I think it Marconi brought all these different facets together and exploited it in a commercial sense. Pardon? Well, just out of interest, Kelvin's brought up a name called Nikola Tesla. And in the 19th century, there was a commercial battle between two guys. One was Nikola Tesla, who I think he was American-based, but he originated from Eastern Europe, might have been Czechoslovakia or something like that, I'm not sure. Do I have another slide? Anyway, we digress. So there was Nikola Tesla and a guy called Thomas Edison. Now, both of them worked on electricity and the transport of electricity over great distances. And this is, the gentleman has just said it there. Thomas Edison, he founded all his products on DC electrical current, that's direct electrical current. If you get a car battery and you hook up your heart monitor to a car battery, all you see is a straight line. It doesn't change at all. That's direct current, it's going direct. Alternating current, as we've seen on a sine wave, fluctuates. It alternates positive and negative at either 60 hertz or 50 hertz. Now, the argument was, which was the most efficient to distribute over long distances. And the problem with DC, direct current, is its propensity to being reduced due to electrical resistance in the wire. So over long distances, you might start off with 240 volts at a generator, but because of electrical resistance at the user, it might be 100. That's the problem. That's not the case in alternating current. You can transmit alternating current over long distances. There's still electrical resistance plays part, but the transmission of alternating current is a lot more efficient than DC current, and that's why we have adopted alternating current today. However, given the advances of technology, in the United Kingdom now, we import a lot of electrical power from Europe, and we do that through high voltage DC cables. And these are big cables, and we're talking about high voltages, really high, 150,000 volts and above. But at that level, the electrical resistance has the effect to reduce current to a small level. So we can transport the energy more efficiently DC than we can at AC. And we do that because we've got the technology to convert it at either end. So like I introduced about the offshore wind farm, we have 54 wind turbines generating 50 megawatts of alternating current. Offshore we have this platform which converts it to DC, shoots down the line. At the other end on land we've got another platform which converts it back to AC, which goes on to the national grid. That's how we do it. Yes, sir.
Better an explanation. Amplitude modulation against frequency.
Right, the gentleman's asking me about amplitude modulation and frequency modulation. And basically we recognise that as AM or FM. So, if you can recall the slide where we showed the sine wave, like this, its peak is called its amplitude. So it can be have a positive amplitude, or it can have a negative amplitude. So in amplitude modulation, what we do is we vary the amplitude of that signal. So if I was talking, as I am now, if you looked at it electrically, you'd see, as my voice went high, it could go high, and when my voice went low, it could go low. So you'd see a variance in the amplitude. Yeah? In contradistinction to that, frequency modulation is we impose our voice in an electronic sense on the frequency of the wave. So can you remember them springs, them sling, like in, what's that film where he's in? Toy Story. Mr. Slinky, these long slings. If you get hold of one end and you physically move it, you see that wave go through the spring. So the amplitude's not changing, but the frequency is changing. So we impress the communication, our voice, onto a carrier wave, which is the slinky spring, and it's decoded at the other end. Does that make sense? Yes, sir.
If it's not too far afield, earlier this week, I was impressed with your knowledge about the JFK assassination.
Yes.
I wonder if you could just summarize, tell us who did it.
Now, has anybody got a Kakano rifle in the audience? I introduced 2 books. The gentleman's asking me to expand on JFK's assassination. And I introduced 2 books. One's by an Australian detective called Colin McLaren. And he references another book by a guy called Boner. Forgot his name, but they're on the slides. And this guy, Boner, German guy, I think, Herringer, uses a lot of information from a ballistic expert called Howard Donahue. And apparently, after the McLaren report or something like that had been published, some top ballistics experts in the US were called together and they built a tower which was at the same height as the book depository, and they also replicated the course of President Kennedy's car down Dealey Plaza at the speed and at the same inclination. And the ballistic experts were each given a Kakano rifle, which does not exactly, but the same make that Lee Harvey Oswald used. And the task was to, in the time period, load 3 bullets, fire them off and see if they could hit the target. And there were only 2 people who could actually do that, or did it, and one of them was this guy, Howard Donahue. And it sparked his interest in the possible causation of the assassination of President Kennedy. And he came to the conclusion, he also looked at the bullets that Lee Harvey Oswald used, and they were high velocity, body penetrating bullets. And we've all heard about this particular shot that went through President Kennedy, moved, and then went through the governor in front, and then embodied it. So I can't remember the exact details of this, but excuse me. He goes into all these different shots and the trajectory, and McLaren, the detective, also builds on this. And basically, they say that one shot got nowhere, it hit the floor, and there's evidence of the smell of the heat generated from this particular bullet. The second bullet went through President Kennedy, as we've seen. Can't remember what happened to the 3rd bullet. I'll have to read the book again. But what's interesting is the bullet that actually killed President Kennedy, and you've all seen this film, this is the Bruder film. And you saw the reaction of President Kennedy, and he fell forward and people started to be alarmed. And then the shot that actually killed him basically threw him back this way, and the top of his head came. Yep, I'm sorry, but that's what happened. Then Donahue argued argues the case that this is a totally different bullet. It's an explosive bullet, which means that when it hit the head, instead of going right through cleanly, it actually exploded. Poof. Now, these particular bullets were used. Now, no one's got. Anyway, these particular bullets were used by the US Secret Service, and they came from a particular rifle. I think it's a A-17 automatic rifle or whatever. And Colin McLaren and both this Bona Horinger or something. Yeah. They go into the background of the Secret Service, and particularly the guys. They've got all the names from the Warren Report. And they know that these guys on the day before, they were up at 4 o'clock in the morning in a bar drinking, so they weren't in top performance to be Secret Service engines. There was a guy sat in the car behind who was not normally a Secret Service agent who had authority to have this particular type of rifle on him, but he did on this occasion. And there was no safety on it. How they established that, I don't know. But when these shots went off, this guy stood up with his rifle, and they surmised that accidentally, because there was no, he went off and blew President Kennedy's head off. Now, okay, that's that might have been what happened. But if you read these books, they go into the circumstances with the Secret Service before the incident, and then what happened afterwards when President Kennedy's body was taken into the autopsy room, the things about bullets going missing, the things about forensic evidence going missing, and the fact that Secret Service agents were there at the time in the autopsy room. And all this is brought together in what I think is a fairly convincing account of what could happen. Now, it's only an account, and as we know, in a court, you can't establish beyond reasonable doubt that that happened, but I just got this gut feeling that that's what happened. Is that all right?